Greetings, and thank you for joining me in the Subsurface Drainage Basics module. In this module, we'll start with discussing why we even need to do drainage, and then we'll follow that with a history of drainage and the extent of drained lands. We'll talk some about drainage types and drainage terms and parts and pieces. We'll end with a discussion of standards because we can use an ASAPE standard for drainage design, but there are also conservation practice standards that we'll use for our conservation practices. We'll start this lesson with why do we even need to do tile drainage?
As I said this before in this course, the most important part of getting agriculture, one of the most important parts of getting agriculture right is managing the water right. When you don't have enough water, you irrigate. When you have too much water, you improve the drainage. And that sets the context for this entire week, especially this first lesson where we're talking about why drainage. And to open this first lesson, I want to show you some results from a survey I saw on Twitter about 2 years ago. I'm sure this wasn't a scientific survey, and I don't know what this company necessarily sells, but this company asked farmers on Twitter, what have you done on your farm that has provided the highest return on investment, ROI? What have you done that has consistently provided a positive return on investment? What sort of investment have you made? And as a drainage person, I wanted to know, did any farmers say tile drainage? So as I started scrolling through the results, sure enough, I saw things like tile drainage, for sure, from a farmer in Ohio, tile, besides tile and grain storage from a farmer in Western Illinois, and I kept scrolling and I kept seeing pattern tile, tile from farmers across the Midwest. And so there's clearly something to this idea that farmers consistently see a real benefit to improving the drainage by installing subsurface drain pipes in this part of the world, in this Midwest United States. The definition of improving the land drainage, the practice of improving the land drainage, is the removal of excess water from the ground surface or from the root zone, including removal of soluble salts from the soil to enhance crop growth. There's a couple of key points here. Removal of excess water. So we're talking about removing, in subsurface drainage, removing the gravitational water from the soil, which we talked about in some of the soil water concepts, what is gravitational water. And then our entire focus, the second part of the definition, our entire focus is to enhance crop growth. We'll talk about that more in a minute in terms of crop growth. Many areas have natural drainage. Many agricultural areas have natural drainage. This means that excess water flows from fields to swamps to lakes, to lakes or to rivers naturally. Natural drainage, however, is often inadequate, and so we artificially improve the drainage, or we create a man-made drainage system. Sometimes the word artificial takes on negative connotation, like artificial ingredients in something, you know, if you're a proponent of organic or naturally sourced ingredients. But in this case, the word artificial is just an honest statement that man has improved the drainage. Poor drainage is caused by a couple different things, or a combination of a couple different factors. First of all, poor drainage can be caused by excess precipitation, having too much rain or snow at the wrong time or in the wrong place. Poor drainage can also be caused by soils with poor permeability rates. Permeability is the ability to transmit water through the root zone. This is especially true for us in our case here in Illinois, where we have a restrictive layer underground, a layer with poor permeability, not right at the surface, but a couple feet underground below us, and that doesn't let water percolate downward. So this creates what we call a perched water table. So it's not that all of our soil has poor permeability, we have a layer of soil with poor permeability about 3 or 4 feet down. And then we also have poor drainage can be caused by poorly developed surface drainage topography. You know, if it's flat, then water's not going to run off. It's not going to drain naturally. And so you can have poor drainage caused by lack of surface topography. So coming back to why drainage? Why do we improve the drainage? There's two main reasons for crop yield reductions with waterlogged soils. First of all, plant roots need oxygen for respiration. Roots are just like little microbes that require oxygen to breathe. When oxygen is consumed faster in the soil than it's exchanged with the atmosphere, then things like waterlogged soils happen. which leads to hypoxic conditions in the soil. We talked about hypoxia a couple weeks ago when we talked about the hypoxic zone in the Gulf of Mexico. This is the same exact idea. Hypoxia means low oxygen. Here, when we have hypoxia in the soil, it's the same thing. It's just at a very, very, very small scale compared to the Gulf of Mexico hypoxic zone. Same idea though, low oxygen or O2 limited conditions in the soil, in waterlogged conditions. The most basic consequence of excessive soil water is the restriction of the supply of oxygen to the roots by displacing air in that pore space, replacing air with water in that pore space, which I'm just illustrating on the screen. But this actually raises an important point. Water by itself is not harmful to crops, and in fact, if you think about hydroponics, plants can grow in total water culture as long as you're supplying oxygen. So like think about hydroponics. Hydroponics use either oxygenated water. So remember from our dissolved oxygen lesson in the first week, in the first set of lessons, if you bubble dissolved oxygen through the water, then that provides oxygen for the plant roots, even though they're growing in pure water. Or sometimes in hydroponics, we do cycles of submerging the roots and then drying the roots and submerging the roots and drying the roots. But again, water by itself is not harmful to plant roots. And so this kind of flips my idea of drainage on its head, because we're always talking about improving the drainage where we're removing water. We have too much water, but that's actually not the issue with drainage. We want to use drainage to supply oxygen. It's not an issue of too much water, actually. It's an issue of not enough oxygen. So I wanted to put that in context. If you're thinking about this from the plant root perspective, that's important context. So let's put some science to this idea. This graph shows that as you have waterlogged conditions for longer periods in the soil, as your duration of waterlogging increases, your oxygen level in the soil declines, and that decline is actually pretty rapid. Oxygen concentrations in the range of 8 to 14%, so around here on the y-axis, have been reported as a minimum for unrestricted root respiration. Now those actual values will depend on the crop and the growth stage and the soil temperature and a lot of other factors, but keep in mind there's a minimum oxygen concentration that plant roots need to be able to function. This graph also nicely illustrates that as the soil temperature increases from 43 Fahrenheit all the way up to 64 Fahrenheit, the percent oxygen concentration in the soil decreases as you get warmer and warmer temperatures. For example, relatively cooler temperatures, after 10 days of waterlogging, you have relatively more oxygen in the soil remaining compared to warmer temperatures. And that's because the microbes in the soil and the other processes in the soil speed up and use up that oxygen. There's clear negative impacts on plant growth and, for example, germination or seedling emergence, as you see here, with relatively short periods of waterlogging. Oxygen content in the root zone often drops below critical levels or can drop below critical levels for plant growth or seedling emergence within hours of waterlogging. So we're talking 4 or 6 or 8 hours of waterlogging, and you could potentially start to see crop yield impact. The seeds of many species themselves can tolerate short periods of limited aeration, but when you get into periods of cell division and growth and germination for the plant roots, these processes are severely reduced when you have a limited supply of O2 getting to them. And that's the whole concern with the waterlogged soils. There's just not enough O2 getting to those plant roots. And here's a similar figure. This is for wheat. The previous one was for corn. After 4 days of flooded soil, you're down to about a 50% yield. So you can see that, and that's really a massive crop failure. 50% of your yield is not something that's okay with our farmers. Scaling up from seedling emergence to the actual end of the season and actual crop yield, which you see here, this is percent relative yield on the y-axis. This graph just nicely illustrates the important yield penalty that you get for a variety of crops. When you have, for example, just 2 days of waterlogging based on these data, you're below 80% yield for cotton. Corn is down to below 70% yield just after 2 days of waterlogging. So in a practical sense, driving around in the spring when it's wet, especially after a rain, it's not uncommon to see standing water in our lowest parts of our fields for 24 hours. You drive by the next day, 36 hours, 48 hours. It's not uncommon to see waterlogged parts of our fields. And so this information right here on this graph is very relevant for us because we don't want waterlogging lasting 1, 2, 3, 5, 8 days for sure. So bringing it back to our text, poor aeration in the soil leads to a variety of related negative consequences, which you can read the bullet points there. But really the important thing is that you want good aeration. Good aeration favors root activity, it makes plant nutrients available, it leads to a better balance in the soil overall. And then this says there's two main reasons for crop yield reductions with waterlogged soils, and the second reason is the inability to plant and tend the crop at the right time. So this is more of a human-related factor. We can't get into the field when it's too wet. I've showed you this graph before in an earlier lesson. Corn in particular is sensitive to delays in planting past a critical threshold date. And this type of idea, critical threshold date, isn't a new idea. Here's older data for influence of planting delays on corn in North Carolina. And you can see as you get past that optimum planting date, even if you're 2 weeks late, you're going to achieve 90% of your potential maximum yield. And that's if every other thing during the growing season goes right. So that's just really not acceptable. Thinking back to those farmer survey results from Twitter, that Twitter survey, clearly this is why farmers want to improve the drainage. This is something that's within our control to do to make sure that we're getting into the field in a more timely manner. Now, if planting gets delayed because the field is too wet, this planting bar will get shifted to the right. The impacts there include it starts to get too hot. If that red bar is shifted, it starts to get too hot during critical growth stages for the corn to do well. You'll also have a period of grain ripening and grain fill, which is later in the summer. That starts to occur during shorter days rather than slightly longer days, and that potentially reduces the period of time available for those grain fill and grain ripening processes to occur. So one of the primary functions of a drainage system is to provide trafficable conditions suitable for all of these springtime operations. This is a very busy time of the year, and so drainage allows some of these operations to occur. I also want to talk about a few kind of benefits-ish. I put benefits-ish because this is a little bit of a mixed bag, starting with the impacts on soil temperature, the impacts of artificially draining our soils, the impact on soil temperature. Soil temperature is very important for seed germination in the spring. The soil has to be warm enough for the seeds to germinate, and sometimes you hear anecdotally a benefit of subsurface drainage is that your field will warm up faster. This hasn't really been proven out through research. Like I said, it's kind of a mixed bag, so there's complicating factors on both sides. For example, if you think about the specific heat of water, which we covered in our physical properties of water lesson in one of the first weeks, the specific heat of water is very high. It takes a lot of heat to warm up 1 gram of water by 1 degree Celsius. It takes a lot of energy to warm up water because it has a high specific heat. So it takes a lot of heat to warm a wet soil versus a dry soil. And this is probably the strongest argument for the fact that a tile drain field will warm up faster than a non-tiled field. But there's also an argument that if your soil is wet, it'll be darker, and so that would warm up faster because a darker soil will absorb more solar radiation, right? I mean, that's, black absorbs heat better than white, so darker soil could absorb more solar radiation compared to a well-drained or a tile-drained, lighter colored soil. And then there's another argument, undrained soils might warm up faster because water transmits heat better than air, or water transmits energy or heat better than air. So this is all very kind of complicated. You could probably do an energy balance on this if you really wanted to. But in short, you hear time and time again that draining the soil provides a heat benefit. It hasn't really been proven out in research, but anecdotally you will hear this all the time, that draining the soil will help warm your field up faster in the spring. Now there's a few other benefits of improving subsurface drainage or installing subsurface drain pipes, and this is actually includes a benefit to water quality. Improving the drainage means this is an overlooked benefit, but improving the drainage means that, of course, when you get a rainfall, the top of the soil profile is dry, and so you provide a place for storage in subsequent rainfalls because you've dried out the soil profile. Now, if you don't have a drain field, when you have a rainfall, the soil surface will be wet, and then you'll end up having runoff rather than having a place to store soil moisture under those undrained conditions. Now, this runoff is a concern because it causes erosion. You're losing sediment from your field, and then you're losing sediment-bound pollutants like phosphorus. So that's not great. This is kind of a forgotten benefit of subsurface drainage, that you can actually improve the water quality if your primary concern is erosion and phosphorus. We've created a trade-off though, because we know that subsurface drainage also carries nitrogen with it and sometimes phosphorus, so there's just a trade-off here. Obviously, improving the drainage or installing subsurface drainage has also led to a loss of wetlands. More than 50% of wetlands in the United States have disappeared because we've improved the drainage and made other land use changes. This has had an impact on migratory birds and countless other untold effects on our natural environment, because wetlands are kind of the kidney of the water cycle, or kidney of the water system. And so this is definitely not a benefit that we've lost a lot of wetlands. There's definitely a trade-off here. Then there's always lots of questions about, does drainage cause flooding? So this is a kind of a benefit-ish. This is a question that pops up every time we get flooding. And the answer to this question, does drainage cause flooding, is twofold. One, it depends, and two, it's complicated, which aren't very good answers because they're kind of non-answers. But the rationale is that, in general, installing subsurface drains will reduce your peak runoff rate and reduce surface runoff overall, again, because we've provided a place to store that rain when it happens by drying the soil profile, but you may actually lengthen the storm hydrograph. Okay, so again, it depends, and it's complicated. It depends on antecedent initial soil moisture. How wet is the soil when you get that rainfall? And just keep in mind, if you get 6 inches of rain in an hour, you're going to have flooding, drained or undrained. And people tend to forget that. If you get a lot of rain in a short amount of time, you're just going to have flooding, drained or undrained. And so, does drainage cause flooding? This question pops up all the time. And the answers are, it depends, and it's complicated. Now, one last thing I want to cover, the sanitation benefit of drainage. This is something that we often forget about here in the Midwest, in this developed country that we live in. But historically, drainage was a big public health issue. Eliminating stagnant pools of water is a public health issue because you want to reduce areas of stagnant pools that mosquitoes will breed in. So I like this photograph from the Centers for Disease Control, the CDC, 1920s photograph taken somewhere in the southern United States. They were digging a drainage ditch to reduce stagnant pools of standing water. Again, the concern here was that you don't want places for mosquitoes to breed, because those mosquitoes will be vectors or carriers for diseases like malaria and other pretty nasty diseases that are human health risk, as well as a risk to livestock health. So I think this is the sanitation benefit is important to mention, even though it's slightly less relevant for us here in a developed country today. See you next time.